All right, I am going to pull up the next PowerPoint. All right, so chapter 6, I would like to go through pretty quickly. If we can't, we can't. But at the end of the day, like, there's not too many questions that you're going to really get asked on it because there's really not that much that's, I guess, testable. But I really think that's kind of a shame because I really do think this is one of the more important chapters to kind of understand for those of you who are like me and are like a pre-med who are going to be taking like biochemistry courses down the road. Like this chapter is like uber important for that. Just because like spontaneous versus non-spontaneous reactions within the body are like super duper important. Understanding how enzymes kind of like are made to increase entropy despite literally their jobs being increasing order. It's just really kind of cool. And understanding thermodynamics and kinetics is really useful for that. Okay. All right. So first things first, you guys need to know some of this stuff. So HV is literally just going to be light. Okay. And then delta, that symbol is mean heat. Okay. A solvent is going to be written below your reaction arrow. Understand that solvents usually do not participate in the reaction. Sometimes you can have what's called solvolysis, where like literally the solvent is the reagent. But if you're given the solvent and something else, I want you mostly thinking that, okay, this other thing is going to be the one reacting. Okay. So components of a reaction formula. So that black arrow at the bottom. I have a reactant on the left side, a reagent above. Sometimes you'll have a solvent down here. Sometimes it'll be heat or light. Okay. And then over on the right side over here is your product. Okay. This shouldn't be too complex. Sometimes what you're going to see is this. You're going to have a reactant over here, and you're going to have reagent and reagent. Okay. That means that in step 1, we are using this reagent. In step 2, we are using a different one. Make sure that you have that parenthesis outside of it to separate it, right? If you don't, that could mean that you have that you're trying to communicate that you have 2 equivalents of something, and that's not what we're trying to do here. Okay. All right. Again, this is just gonna practice on what we just did. So over here on this side, that's our reactant, that's our substrate. This is our reagent. Light is a condition. And then over here are our products. Okay. This, at least the first 3, are seemingly not important. However, when we get into what's called synthesis, which is going to be later down the road, which is one of the hardest, most difficult, and unfortunately like unteachable things, you have to kind of rely on your understanding of is this substitution, elimination, addition as a first step. Okay. Yes, indeed. So let's go through it. What's a substitution? A substitution is going to be text plus 1 and minus 1 sigma bond. Basically, what I'm trying to get to is we are removing 1 sigma bond and then adding another. Okay. In a substitution, right? We're substituting 1 bond for another. All right. In elimination, I am subtracting 2 sigma bonds and I am adding 1 pi bond. Okay. And then addition. Add 2 sigma bonds, remove 1 pi bond. Okay. Make sense? Okay. I'm not too concerned with 5 or 6 like at all. At least not yet. Yes, acid-base reactions are important, but for Orgo, I think that like they're kind of okay. They are important, but substitution, elimination, and addition are way more complex. Okay. And there's way more that we can do. Okay. Whereas acid and base is literally just one thing deprotonates here, one thing adds here. I'm sorry, one thing deprotonates this. Like there's not much. Whereas I can add like a dozen, maybe 2 dozen sets of reagents to a pi bond, and they're all going to result in different products. And you guys will need to know that moving forward, but not yet. For now, I want you really understanding substitution, elimination, and addition. Okay. Any questions so far? Okay. Okay. A is what? All right, good job. B. Very good. C. Okay. So everybody thinks that C is addition, correct? C as in carrot, right? Okay. Interesting. Does anybody have a dissenting opinion? I like controversy. I like drama. Thank you. Very good. That is correct. It is a substitution reaction. Did the number of pi bonds change? No. Therefore, it's really hard for me to say it's addition, right? This one is particularly difficult because you don't have the hydrogen shown to you, and you need to really like kind of see what you're doing in order to get this one right. So yes, the answer to C is substitution. We start with a pi bond, we end without one. Right, so we're subtracting a pi bond, we're adding 2 hydrogens. Make sense? Great. Okay. We're not going to do D. I didn't want to do that. Reaction mechanisms. This is like the bread and butter of Orgo. Like when you hear someone complain about organic chemistry, they're probably talking about mechanisms. It's like the most iconic thing about organic chemistry. One of the problems with mechanisms is that people kind of try to memorize their way through them, which might work for now. But as we go further and further, we get to chapters with like a few dozen reactions. So memorizing a mech isn't going to work out. It's just not. So there's a few things that we can do to kind of play around that. Okay. But for now, we're going to do the basics. Okay. So a barbed arrow is going to look like this. Okay. That's the movement of one electron. We do not really see that until yeah, I can do that, Alex. Let me finish this slide real quick. The barbed arrow shows the movement of one electron. The double, 2. Concerted means single step. Stepwise means multiple. Okay. In a stepwise mech, we create intermediates that are then consumed in the next reaction. Okay. Okay. All right. So in A, I am breaking this one. Yes, concerted would be like a proton transfer. This is then made. I'm cutting out this carbon-oxygen double bond to add this bond and this bond. Okay. Over here, I am cutting this bond to make this bond. Okay. And then over here, I am cutting this bond. And I'm cutting this bond to make the double bond. Okay. Here's a little chart. What in the world? No, it ain't. This is nonsense right here. It is a half-headed arrow. This is not until you get to biochem. I don't want you worrying about that until then. For Orgo 1, if you have a reaction arrow, it is this reaction arrow. Do not concern yourself with the other things, okay? That's for Orgo 2. That's for biochem. It's not for now, okay? Okay. What in the world? Do be. So we have a negatively charged bromine, which is an electron-rich species, which is a nucleophile, and a carbocation, which is an electron-poor electrophile. Nucleophiles attack electrophiles, resulting in this. Okay. Terms for bond breaking. There is homolysis and heterolysis. Homolysis is the breaking of a bond that results in both atoms getting the same number of electrons, one. Okay. Heterolysis is one gets both electrons. Okay. No. Do see. I want to see what you guys get. Did you guys break here? Did you guys break here? Did you guys break in pink? Or did you break in green? So which one? The first one's red, all the way on the left side, then blue, then pink, then green. What you guys do? Okay. Get a mixture of answers. You get some blues, some pinks, okay? All right. I think it's gonna be blue. And here is why. If I break here, I get a carbocation at this position. That is an allylic carbocation that is going to be stabilized by resonance. Therefore, it will be a very stable intermediate, and that's really good. Furthermore, if I break at pink, I never mind, that's not true. Yeah, pretty much if I do anything else, I end up getting a weird set of charges somewhere. But like if I broke it pink, I don't end up getting the resonance stabilized carbocation, right? And so therefore I don't really want to cut it pink. Okay. It was a good choice, but I don't think that's gonna happen. Okay. Yeah, definitely. All right, makes sense. Yes, when you break the blue bond, the electrons return to the oxygen because the oxygen is more electronegative. Awesome. All right. Bond dissociation energy. So increasing strength, increasing dissociation energy. Bond dissociation energy means the amount of energy that I need to put into my system in order to break the bond. When you guys think of bonds, think of a stick. Okay. If I want to break the stick, I need to put energy into it by bending it, right? That's the same way that that systems break bonds. Okay. They take energy from the surroundings and then they're going to use that to break their bonds. Okay. Meaning the process of breaking bonds is going to be endothermic, or delta H is going to be positive, and the process of forming them is going to be exothermic, or delta H will be negative. Okay. Here is a periodic trend. Okay. Why? For those of you who have taken physics, you might remember that that opposite charges attract with a certain force. And then that force is also going to be related to the energy that they attract one another. Okay. The closer that those two things are to each other, the stronger that interaction, the harder it is to break. Okay. So the whole reason that as we go down, we have a lower dissociation energy is that the bigger the atom, the farther away the electrons are from the nucleus, meaning the farther away the bond is. Okay. The farther away, the less energy that the two dislike ions, not ions, charges attract, the easier it is to separate them. Okay. Okay. On your test day, I can almost guarantee this is going to be a question where you are going to need to calculate the delta H of reaction. Okay. A lot of people kind of struggle with this. I'm going to give you the equation. It is going to be delta H equals bonds broken minus bonds formed. Okay. This formula is going to help you do that. Okay. All right. Here are just some values. Okay. Oh, here, I'll write it up again. My bad. I'm sorry. H is going to be bonds broken, which is positive, minus I hope so. I can't guarantee it. We'll see if the computer agrees with me. Right. Clear all drawings. So that's the periodic trend we were just talking about. Actually, this is different. This is the trend for atomic radii. Not too important. Yeah, so just using the trends in A. Finally, someone freaked out. No, you don't. Dr. Dowdy likes to screw with you, so I like to screw with you. But no, you don't need to memorize any of that nonsense. Don't worry about it. All right, so here, which has the higher dissociation energy? In A, just do A. A or B? Okay. Any dissenting opinions? Okay. Okay. All right. Some drama, some controversy. Okay. So the oxygen is smaller than the sulfur. Therefore, the oxygen actually holds the electrons closer to its nucleus. Okay. Positive nucleus, negative electrons in the bond closer. Therefore, they're harder to break, harder to separate, right? Therefore, the answer should be A. Okay. All right. B is more unit one, so I don't want to cover it. It's going to be the carbonyl because double bonds are stronger than single bonds. Yes. Oxygen above, therefore it's smaller. Therefore it has higher bond dissociation energy. Does it make sense? Nice. Um, um, Row 4, dissociation energy decreases if we go down the periodic table. Yeah. Yeah, unfortunately, I really kind of wish that physics was a prereq for chem. And I know I'm probably like the only one here who thinks that, but like if you understand physics really well, which like I don't, um, chemistry becomes way easier, especially orgo. Because orgo is literally just like positive thing, negative thing, reaction. And like physics gonna tells you how to quantify that, which is really cool. Um, okay, just do A. Okay. Feel free to look at this chart, okay? What you guys can. right? So just quickly wrote out the bonds that you're going to be focusing on, right? So this here is going to be bonds broken. And then over on the right, formed. Pretty much, basically because like we need to kind of break the bonds that we have in our reactants to form new ones, right? So in general, we're going to be breaking bonds on our reactant side. Okay. All right, let me go use slide 14 real quick. Yeah, you guys are about right. It would be about 42. Okay. And so therefore it would be endothermic. $293 for CBR. I have no idea what kind of calculator you're allowed to use. In my opinion, you guys don't need one. It's literally just like this number plus this number, right? You're just gonna like, you can just add them manually, you know? Okay. Okay. We're gonna do a really quick overview of thermodynamics. So basically when we're talking about thermodynamics, I want you guys thinking about like equilibrium constant, Gibbs free energy, enthalpy, and entropy. And that's pretty much all you really need for this class. Okay. So equilibrium constant. The equilibrium constant is a formula that shows you the concentration of your products divided by the concentration of your reactants. Okay. If your equilibrium constant is if it is greater than 1, you have more products than reactants, and therefore the reaction is favorable. Okay. If it is less than 1, the reaction is unfavorable because you have more reactants than products at equilibrium. All right. If it is equal to 1, the system is at equilibrium. All right. Gibbs free energy is defined as like something stupid, like Gibbs free energy is the free energy associated with the reaction, which I don't know. It doesn't make much sense, but that is the definition. Enthalpy. When you hear the word enthalpy, I want you thinking heat. Okay. It's just the heat associated with the reaction. It can be exo or endothermic. If delta H is negative, it will be exothermic. If it is positive, it will be endothermic. Okay. Thermodynamics are not kinetics, and kinetics are not thermodynamics. You will save yourself so much headache by getting that straight now. Okay. Rate and thermodynamics are not the same. Thermodynamics has to do with equilibrium, spontaneity, heat, kinetics, how fast something goes. You cannot use thermodynamics to predict the speed at which something goes. I will give you an example. A lot of you probably have like a bag or a box of sugar stuffed into your pantry, right? The reaction of that sugar into carbon dioxide and water is spontaneous. The delta G is negative. Okay. But if you go to that bag 10 minutes from now or a year from now, there's a pretty good certainty that it won't be much different, right? That's because the reaction is incredibly slow. Okay. There is a difference. Make sure you don't get them confused. Entropy. I use a different definition of this now, but this is how I used to think of entropy, but now I think of it more as the tendency of energy to spread out. Okay. Here's what I mean by that. We know that the universe is always expanding, right? Because how? Because we know that energy is always spreading out. Therefore, we know that entropy also always has to be positive. We know that entropy always has to be positive, so therefore energy is always spreading out, so the universe is always expanding. You can see how that logic is set up. Okay. The other definition is what I have here, which kind of says that entropy is all about disorder. That definitely works. Okay. It's not like this definition is wrong. But for me, it was more easy to understand the other definition that I gave before. Okay. Okay. Okay, before we move on, there are two events that are really important in this class that are going to increase entropy. Okay. If I have a compound AB and that breaks up into more molecules, the randomness increases because I have increasing number of molecules. So the delta S is positive, the delta S of the system. Okay. If I go from a cyclic reactant to an acyclic product, entropy also increases. Okay. Okay. This is a really useful chart that I want you guys to know. I want you to know it for this class, and I want you to know for definitely biochem. Okay. Given each value, determine whether the starting material or product is favored at equilibrium. What's up? Entropy. Okay. If KEQ is 0.5, what is favored, reactants or products? Yes, controversy. Never mind. Okay. Anybody think products? Really, no products. Okay. Okay, there we go. Controversy. Okay. So there's a few ways to look at this. Number one is just to memorize that if K is below 1, then it is going to favor the reactants. The other is how I like to do it, which is to look at it more mathematically. Okay. 1/2 equals products over reactants. In order to get these two things to be equal to one another, reactants must be greater than products. Okay. Does that make sense? Because if there were more products than reactants, K would be above 1. Right? Because if I have 2 divided by 1, right, 2 products to 1 reactant, the value would be 2. Okay. Awesome. Okay. If delta G is negative 100, does that favor the reactants or products? Everybody is unanimously products. There's not a single person that thinks it's reactants. Yes. Okay. All right. Yeah. Y'all are right. Good job. That is indeed, it is going to favor the products heavily, very heavily. Last one we'll do for now is gonna be C. What do you guys think? Will it favor the products or the reactants? Finally, controversy. Good, good, good. Ooh, and he gave an explanation. Yeah, reactants, because it is endothermic. There's a few ways to approach this. Number one, endothermic processes, they kind of rely on something else giving them energy. Therefore, they're just less likely to happen than something that doesn't need that. Does it make sense? Okay, the other way to think about it is more mathematically. And again, that's kind of how I like to think about it. I know that delta G equals delta H minus T delta S. Okay. Since I don't have any information about T delta S, I am just going to have to make the approximation that delta G equals delta H. Okay. Therefore, delta G is positive because delta H is positive. And because delta G is positive, it is not favored to go to the products. It will stay at the reactant side. Okay. Okay. Does that make sense to everyone? What we just did? Good. Good. Again, thank you for everyone for participating in everything. It's all very appreciated. Now we're gonna kind of get into getting into energy diagrams. Okay, so this symbol right here, I have no idea what it means, but it goes in the top right corner of the structure that you draw when you're drawing a transition state. Okay, so if Dr. Dottie asked you to draw the transition state of something, you draw brackets, the thing, and then that thing, the symbol. Okay. But that said, I know that other professors like to ask transition state questions. I don't think Dr. Dowdy likes them. Okay. However, I want you guys being able to identify transition states, energy of activation, intermediates, reactants, products, and the delta H of the reaction given an energy diagram. Okay. You will also be expected to understand whether a process is concerted or stepwise based off an energy diagram. Okay. And I want to show you how to do that now. So, first of all, let's start. Let's write our reactants, our products. Okay. Reactant, product. Everyone agree? Okay. Now, B or C? Is B the intermediate or is C the intermediate? Okay. All right. Everyone who answered it got it right. So C is going to be the intermediate. Why is it the intermediate? Because it is lower in energy. Understand that how like scientists define what an intermediate is. An intermediate is defined as a compound that lasts longer than one electron wave. Okay. That's very, very, very fast. Like we're talking like a millionth of a second. So an intermediate just is going to be lower in energy than a transition state because a transition state doesn't even need to be that. Okay. It doesn't even need to last for a millionth of a second. Okay. And in fact, we do not think that transition states actually exist because they can't be isolated, right? All right. So now we're going to talk about energy of activation. Okay. Going from the reactants or intermediate to the highest peak within that slope is going to give you the energy of activation. Okay. Again, C to D, and then E to F. Those are all energy of activations. Okay. Finally, in green, going from A to G is the delta H of a reaction. Is that exo or endothermic? Okay, it's exothermic. Oh. Oh. So one of the ways that you can calculate delta H, and you won't need to do that, you won't need to calculate it this way in this class, but if you guys are taking the MCAT, you might. It's gonna be delta H products minus reactants. So in a perfect world, I could write this how it should be, but it's going to be H of products minus H of reactants equals delta H. Okay. Okay. Awesome. How many steps are there in the energy diagram? You can tell whether it's exo or endothermic by looking at the reactants energy level and the products energy level and then comparing them. If the products are lower in energy, it is exothermic. If the products are higher in energy, it is endothermic. The question was how many steps are present in the mechanism? Yep, it is 3. From A to C, C to E, E to G. Okay. All right. Let me clear kinetics. This is literally just how fast the reaction is going. Okay. Here is something that like a test question that kind of writes itself. Which of the following is not a factor that affects the rate constant? A, catalysts. B, temperature. C, concentration of reactants. D, energy of activation. Which of the following does not affect the rate constant?
Do you mind repeating the answer choices one more time?
They are written right here. Concentration, temperature, catalysts, energy of activation. That's very interesting. We have a very nice mixture of answers. Okay. Concentration. Concentration does not affect the rate constant. Why? Because, okay, the way that I think about it is this. If concentration affected my rate constant, yeah. Then why would I have concentration in my rate law? You know what I mean? That would kind of be redundant. So therefore, the concentration shouldn't really affect my rate constant. What's kind of stupid about the rate constant is that it's really very, very variable. So if I change the temperature by like 1 degree, my rate constant changes. Okay. If I add in a catalyst or an enzyme, it completely changes. Okay. The energy of activation is less controllable by me though. If I add in a catalyst, catalysts act by decreasing energy of activation, resulting in an increase in rate of reaction. All right. Okay. So all those factors do affect the rate of reaction. Yes. Okay. All right. Rate equations. Number one, if you have a rate determining step, that's your rate law. Okay. The slowest step is going to determine your rate, right? That's why it's called the rate determining step. Got it? Okay. The rate law is going to look something like rate equals K times the concentration of thing 1 times the concentration of thing 2. Okay. Sometimes you can have different orders of reactions where I have something like this and one here. But like for this class, I've only seen it where the maximum order is 2, where it's 2 reactants, both having an order of 1. Okay. Okay. Again, it's the slowest step that determines the rate law. I'm making sure that's it. Did I forget anything? From 6? I think I hit everything. Let me check the textbook really quick. Oh, yeah. That sounds about right. All right. So, I want to go to that. This is where I want to teach you guys how to do MECs. All right. So, a lot of your classmates are going to be like, or a lot of your peers who have taken this class before are probably going to tell you something along the lines of, yeah, just memorize your MECs. They're wrong. I'm going to try and teach you guys how to look at any MEC and just kind of immediately know what it is. Okay. If this will let me annotate, which is a big if. Okay. Okay. So there are a handful of patterns that you need to know. All right. But whenever you look at a MEC, if you just look for these 5 things, you're going to be A-okay. All right. Actually, I'm going to use this for this. I want you looking for acids, bases, nucleophiles, electrophiles, and leaving groups. I want you looking for what in the world? Okay, I don't know why the font looks like that. But I want you looking for those things in that order. Okay. Acid-base reactions are generally more favorable and easier to do than nucleophile electrophile reactions. Therefore, if you have an acid and a base, acid-base will occur. Okay. I also want you looking for the leaving group last, because wherever you have a leaving group, you have an electrophile. And so you want to make sure that you have an electrophile before you draw some leaving group. Okay? Make sense? Okay. So let's see what this looks like. The general acid-base reaction is also called a proton transfer. All right. Now, a lot of you are going to get a proton transfer confused with a nucleophilic attack. In order to keep them straight, I just want you to ask this simple question. Is there a proton being transferred? If the answer to that question is yes, it's a proton transfer, right? Don't just look at the mech and be like, oh, okay, this thing's attacking this thing, right? Ask what it's attacking. If it's attacking a carbon, it's a nucleophile and electrophile. Is it attacking a hydrogen? Then it's going to be a proton transfer, okay? So, B to H, okay? And then this bond is going to break and go to the A, all right? So, the electrons in the base are going to attack the proton, forming this bond over here, right? But the hydrogen is no longer attached to the base. So we need to reflect that change by breaking the covalent bond between the acid and a hydrogen. Okay? Does that make sense? What you can also notice is that the net charge does not change. That is extremely important. Okay? This is still chapter 6, but it's like we're getting into 7. Like this is like a very smooth transition, believe it or not. Funny how that kind of worked out. So I have a leaving group here, right? And it's literally just gonna leave, right? Leaving groups leave. Earth shattering, I know. Okay. These are the patterns. I will now go over carbocation rearrangements and then we'll be on to 7. Okay. Any questions so far?
Oh, just real quick. Does Daddy really care about knowing whether or not it's going to be reversible or irreversible, or will we like get into that more when we get to 7?
We'll get into that more when we get to Orbo 2. For Orbo
Oh.
1, I literally just want you being like every single reaction irreversible.
Okay, awesome. Thank you.
Nice, awesome. Good question. Yeah, it's a mess for Orgo 2. It's not really for this class. Okay. All right. I'm gonna just clear this. Okay. This is gonna be one of the harder things in this class. It's carbocation rearrangements. They're not necessarily hard to understand, but they can be quite difficult to spot when you're in the middle of a test. Okay. So at least for this upcoming test, I want you guys thinking like every single time that you see a carbocation, I want you guys asking, can this rearrange? Can this rearrange? Can this rearrange? Because you can bet that there will be a question when it involves a carbocation, and the only reason that a bunch of students get it wrong is because they didn't see the rearrangement. Okay? So make sure you're looking for it. All right. There are 2 types of carbocation rearrangements that I want you to know. Okay? There's technically 3, but we don't care about the third one. All right? The first is the 1,2 hydride shift. The second is the 1,2 methyl shift. Okay. And first of all, 1,2, they're gonna be right next to each other. It's not 1,3, it's not 1,4, and it's not 1,1. It's 1,2. Can't be anything else. Okay. A hydride is gonna look like, oh boy. Here, let me try this again. Give me 1 second. Ignore the drawing that I just made. A hydride will look like that, and it will be negatively charged. Okay. Okay. Let's go into how that would look. Let's say you have a carbocation here. All right. This hydride is going to attack the carbocation, resulting in its movement to here. Okay. Now, this brings up a good point that I didn't mention earlier. You only rearrange a carbocation if it can be placed in a more stable position. Okay. You don't even rearrangement if it would be just as stable. It has to be more stable. Understood? Okay. All right. 1,2 methyl shift. So the first thing is it's still 1,2. It can't be 1,3. It can't be 1,4 or whatever. It has to be 1,2. Number 2, it has to be a methyl. I believe that we can sometimes get ethyl groups to do this too, but for our purposes as Orgo 1 students, that doesn't happen. Okay. All right. Methyl group is going to come and attack here. That's going to result in this. Okay. Does this make sense? Yes or no? Does chapter 6 make sense? Are there any questions? Okay. It can only happen 1 to 2. It can only occur to be more stable. Yes. Yeah. And yeah, that is the kind of the driving force for why carbocation rearrangements happen. It depends on the substrate given. So like if I look at this one over here with the one under the 1,2 methyl shift, the carbocation can't come over here. So I had to move the methyl in order to give it a more substituted position, right? Whereas in the top one, if I just move the hydrogen, I can get the carbocation in a more substituted position, right? Okay. If there are no more questions, we can take a 5-minute break and then get back to it. Okay. Sorry, I was muted. I am going to be I'm going to be uploading a document, the same document I put up earlier. Okay, that's the document I want you guys to be filling out as we do this, okay? Okay. Okay, so this is the first chapter that we like actually talk about Orga. You know, it's crazy. Like this is the last chapter before the second test, and like we're finally talking about reactions. Okay, finally. So number one, we can only do this with sp3 hybridized carbons. Okay, we cannot do it with sp2, not sp. We can't do it on the benzoic position. It has to be it has to be sp3. Okay, so nomenclature. So say we have chlorine as a substituent. We're going to take chlorine, we're going to take away ine, we're going to add O. So chlorine became chloro. All right. Then we're going to number it, and then we're going to throw it in with the other substituents, and then give it a name. To do A. Okay. All right, when you guys get done with A, let me know. Yeah, sure, that works. Controversy. Okay. Okay. Which is first, C or M? Yeah, C. Therefore, C needs to be listed before methyl. Okay. Other than that, I got you. Other than that, good job, guys. I don't really want to do the others. This is literally just a review of Unit 1. I didn't want to do that. Chapter 7. Okay. Alcohol halide properties. Halogens are very electronegative, okay? There was no stereochemistry, so you can't write configuration. If configuration was given, then yes, you would need to include it. Okay. Halogens are very electronegative. Therefore, carbon halogen bonds are very polar, right? Therefore, because there's a strong polar bond and there's a net dipole, there's dipole-dipole intramolecular forces, okay? Therefore, if I have an alkyl halide, it will have a higher boiling point than an alkane. Okay, so in a substitution reaction, we need a nucleophile and we need a leaving group. Okay, so something to replace the leaving group. That thing is the nucleophile. Okay, leaving group ability is going to be to the right and down the periodic table. Okay, when we think of leaving groups, the goal of a leaving group is to break a bond, right? Well, what's the goal of an acid? To break a bond, right? So when you think leaving group, think conjugate acid. I'm sorry, think acid. Okay. So which is a better leaving group, chlorine or bromine? Very good. Bromine is going to be better. Here's a little chart. Okay. A, which is better, the hydroxyl or the amine? Very good. Very good. OH. B. Very good. Okay. Good job. Good job. Oh. Um, Give me 1 second. In general, nucleophilicity increases with basicity. Okay. Ignore that. The thing that's highlighted in bold, ignore it. Bases of nucleophiles. O is more electronegative, and so therefore it will be more able to hold its negative charge and stabilize it, whereas nitrogen is less electronegative and less able to do so. Bases and nucleophiles, okay? The difference is primarily that bases attack protons, nucleophiles attack carbon, okay? For both, if they're negative, they're stronger, okay? But nucleophiles are more dependent on steric hindrance, okay? Than bases are. Bases are still affected, but not as much, okay? Do all. Do A, B, and C. Oh, I'm so sorry. When did it cut out? Oof, I am so sorry. Um, got it. Okay, so the answers are right, right, left. Okay. So for A, the negative charge, you guys can hear me now, right? Got it. Awesome. So for the A, the negatively charged nitrogen is going to be stronger than a neutrally charged nitrogen. For B, oxygen is wait a minute, the stronger nucleophile. I think it's going to be the nitrogen because the electrons are more loosely held by the nitrogen atom, allowing it to bond easier. Okay. And then for the third one, it's acetate, which is less sterically hindered. So the CH3CO2 is less sterically hindered than CH3. Oh, hold up. I'm so sorry. I did not see that one was CO2 and the other was just oxygen. Okay. So yeah, acetate is gonna be the left. On the right is actually ethoxide, which is gonna be stronger than acetate. I wasn't careful. Okay. So then it's gonna be right, left, right. Okay. So A, right, B, left, C, right. Because let's think of acids really quick. More resonance means more stable, right? Okay, so for C, more resonance, more stable. If I'm more stable, I'm a worse nucleophile, right? On the extra H on the right side, huh? So the more resonance I have in my nucleophile, the worse the nucleophile is. Okay, right? Because it delocalizes the electrons. I want an electron-rich species. So I want all the electrons in one area if I can. Okay. Which is why C is gonna be right. For B, the nitrogen should be stronger in this case, yes. So the nitrogen should be stronger because it's going to hold its electrons more loosely. Because the electrons are more loosely held, they can react easier. Okay. Does it make sense? Kinda. I got you. It's a periodic trend. I'll write it up now. This is for protic, and then the other one's for aprotic. And just in case you couldn't recognize my beautiful drawings, these are periodic tables. Well, the oxygen would be more partially negative. Okay, here's another way to think about it, okay? If I'm electronegative, I'm greedy, right? I want all the electrons for myself, right? Now, if we think of the purpose of a nucleophile, the purpose of a nucleophile is to go form a covalent bond, right? And covalent bonds are shared electrons. If I'm really greedy and really electronegative, am I going to want to share? Does that make more sense? Right. And so in this case, the oxygen is more electronegative, right? It's more greedy. It's going to hold on to its electrons and it's not going to want to share. Whereas the nitrogen is less electronegative. It's more willing to share its electrons to form a covalent bond. Okay? Therefore, it should be a better nucleophile. Does that help? Leaving groups are greedy. Right? Leaving groups are saying, hey, I don't like you. I'm going to steal your electrons and I'm going to get out of here. I'm going to run away. Right? Whereas nucleophiles do the exact opposite thing as leaving groups. They're going to take their electrons and they're going to be very willing to give it away. Less electronegative, the better the nucleophile, which is very weird because most of the time that we see a nucleophile, it's a very electronegative atom. And that's just because the more electronegative the atom, generally the more electron rich it is. So the trends that we see in that, like we see a lot of oxygen things being used in the class, is more so due to the fact that it has a lot of electrons and less so about the fact that it's more electronegative than a lot of things. That is correct. That is correct, Kerner. So, okay, well, hold up. You changed it to something that wasn't. The more electrons that something has, the better the nucleophile it is. It's the stabilization that the electronegativity offers, right? Because if you remember from acids and bases, the more electronegative, the more stable. The more stable, the less reactive. Okay. It does. Look at the top right. Is everybody happy? I can try to explain it in a different way, or again, if you guys would like to, I am more than happy to do so. Let me think. Yeah. Fluorine versus chlorine. Oh, wait a minute. I made a mistake. Yeah, I'm sorry about that. Chlorine. Yep. And guys, in general, if you're not given a solvent, assume it's aprotic. Just as a rule of thumb. Okay. Does this clarify things? Okay. Look, guys, if you have questions, you gotta ask them now. Okay. Correct. And it's only if they don't tell you anything about the solvent. Like if they tell you it's like DMSO, then you need to take that to a product. Or if they give you ethanol, you need to take it to product. But if they don't tell you anything about the solvent, yeah, assume it's a product. Okay. Um, I'm gonna go ahead and move on. All right. All right. Okay. So there are two general types of solvents, polar and non-polar. For now, we're just kind of worried about polar solvents. So there are product solvents and aprotic polar solvents. Okay. So a product solvent can hydrogen bond. A non-protic or aprotic solvent cannot hydrogen bond. That's the only difference between the two. Okay. Um, acetone DMSO and DMF, as well as acetonitrile, common solvents that are going to be aprotic. For common protic solvents, I want you guys thinking like ethanol, methanol, propanol, so on and so forth, as well as water. Basically, any alcohol, any amine, any water, they're going to be the main things that can hydrogen bond. Is it polar protic or aprotic? Okay. 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 B and C. Great. Great, 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 great. So there's no confusion on this. That's good. Okay. Remember, guys, fluorine, oxygen, nitrogen have to be bound to the hydrogen in order to get hydrogen bonding. Okay. Nice. Do A. Okay. I believe so. I believe so. Let me make sure. Oh, I took it down. Okay. Yeah, I believe so. OH or chlorine. Okay. Now we're getting some argument. Okay. All right. So for B in a polar aprotic solvent, I believe the trend is left and down. Up. It'll be left and up. In polar product, it'll be left and down. Oxygen is to the left of chlorine, therefore it'll be oxygen for B. Okay. Makes sense. Make sure you guys correct me. I have a tendency of drawing them wrong and then having to fix them, okay? Okay. Everyone have this down. I did. That's not good. Yes. Originally what happened on that first set was on my on one of my tables I had it going right and then I fixed it to go left. I caught the mistake a couple like a minute or two after I'd made it. So yeah, the reason that it's going to go left is because it's less electronegative and therefore more willing to share its electrons, right? Does that make sense? So they should both be pointing left. Okay. Therefore, sulfur should be better than fluorine. All right, so C is going to be the SH. Okay, reactions. SN2. All right. Guys, whip that chart out that I gave you, okay? So that top cell, I think it's like concerted or stepwise. SN2 is concerted, okay? The second thing that should be on there is like, clear. The second thing that should be on there is like nucleophile or base, nucleophile. Strong or weak, strong. Then I think it's like rate law. Just enter the rate law. It's right here. And then just go through it. So number one, what is unimolecular and bimolecular? Unimolecular and bimolecular refer to how many molecules are in the rate law. Unimolecular is 1, bimolecular is 2. Okay. So concerted and stepwise, concerted is 1 step, stepwise is multiple. Okay. So SN2, let's break down what that means. S, substitution. N, nucleophilic. So it's nucleophilic substitution. What does the 2 mean? 2 means it's bimolecular. On the test, I would really want you taking the substrate given and copying and pasting it into the brackets. Same thing with the nucleophile. Okay, so yeah, you need to write the molecule in. Okay. So in the reaction, the nucleophile is included in the rate. And that's kind of how I conceptualize the fact that the nucleophile needs to be strong. Because it's in the rate law, the identity and concentration matter, right? Whereas for an SN1, it doesn't. And so it's not going to matter, right? It's not in the rate law, so it doesn't matter for the SN1. Okay. Okay. Whack. Okay. That's the mechanism. Okay. Okay. Also lower substitution, either higher substitution, decreasing rate. All right. So you cannot run an SN2 on a tertiary substrate. Know that. Okay. Awesome. Skip that. Okay. Will the first compound or the second compound in A go faster? So let me put it up like this. A, B. Very good. So it's going to be B because B is primary while A is secondary. For B, which is faster. Awesome. Good job. So yeah, so it's going to be A because A is less substituted than B. Right, so increasing substitution, decreasing rate. Oh, so for you're gonna put a product solvent because the apolar product solvent would tightly surround the negatively charged nucleophile, resulting in it kind of be crowded out. So it can't really get to where it needs to go because the water will surround it. For stereochemistry, it is going to result in inversion of stereochemistry. Okay, always. So if I start with S, I end with R. And that only applies to the carbon that you are reacting on. Okay, so like if I have another chiral center somewhere else, it's not going to be impacted. Okay. Okay. Give me 1 second, guys. Okay. So, okay. SN1. The rate law is just including the substrate, okay? And therefore it is unimolecular, right? The mechanism is as follows. Indeed. All right, let me go back. It's gonna be the right one. Oh, I said for B, the first one is less substituted. Yeah, so you're right. Okay. So the first step in the SN1 is going to be loss of leaving group, which is going to result in a carbocation intermediate. All right. That's going to be followed by nucleophilic attack, which is going to result in the final product. All right. Now, a carbocation has what molecular geometry? So there we go. So sp3 is the hybridization, not necessarily a molecular geometry. That's all good. Tertiary is a substitution pattern, not a geometry. Trigonal planar is the correct answer. Okay. So let's take that word planar. Okay. That means it's flat, right? So if something is flat, that means I can hit it from over here and over here with a 50-50% probability. Therefore, I form this enantiomer and this enantiomer in equal concentrations, which is called a racemate. Okay. So the stereochemistry of this reaction is racemization. Okay. Okay. Do B. Okay. So 4B. Those are the two answers. Now, it is very important to note that you cannot draw the first one and then put enantiomer, right? Because this on the right is not the enantiomer of this one. Okay, they are diastereomers. Make sense? Awesome. Good. Okay. So just stability of carbocations, the increase in stability from methyl to tertiary. Okay. Just do the big one, 7.27. Just tell me which is the most stable one, left, middle, or right. Okay. Awesome. Good job. Very good. So yeah, the answer here is going to be the middle one. It's going to be the most stable. I'm going to skip this because I don't really think it's all that important. Basically all it states is that the transition state, which doesn't exist and we don't know what it looks like, will look more like the reactant or product or intermediate that it is closest in energy to. Okay, between its immediate left and immediate right. Okay. This one's really really good one to make sure you guys are ready for the test. So for A, is it going to be left or right? Ooh, I like it. Different answers. Ooh, this is choosy. Okay. In SN1, we want to have stabilization of the carbocation. Therefore, increasing substitution means increasing rate of reaction. Okay. In fact, we cannot even run an SN1 on the answer to the right because it's primary. You cannot do a carbocation formation on a primary or methyl halide. Okay. They cannot go SN1. Okay. So for A, it's the one on the left. What about B? There we go. Any questions about this? Okay. Yeah, the answer for B is left. Yeah. Here's a little graph showing a review of SN1, SN2, but you guys should already have all that one on the Google Doc I gave you. But if you need to make sure, double check anything, it'll be here. We're gonna get into this later because you guys have this really, really, really nice chart that helps a lot. When I took the class, we didn't get that. We didn't have it in our book. So we just had to figure it out. Okay. I know it says chapter 8. It's not, it's chapter 7 for you guys, okay? Just when I took the class, it was chapter 8. Anybody have any questions on substitution reactions? Okay. All right. Sounds good. Okay. We're going to take a 5-minute break, okay? I'll be back in a little bit. Okay, let me go figure out what my channel is called. Okay, yeah. So it is. Let me make sure I can type it in and it'll come up. What row? Not even close. Yeah, so it should just come up as Daniel the TA, but like it's not showing. Um, there is the profile picture is just a molecule of dopamine. So it should just be a little benzene with two OHs and a carbon with nitrogen on it. A few carbons with a nitrogen on it. Spaces. Again, like I hope it works, but like I'm not sure. And there's also there's also always a chance that like everything is fine. You look it up and it won't come up just because like I have no videos, no views or anything like that. So the YouTube algorithm would probably make it hard to find anyway. All right. Okay. Chapter 8. Hopefully after I post something on it, it'll become visible. Hopefully. We'll see. Um, let me check. All right, yeah. I'll have to figure out that some other time. But yeah, Daniel the TA. Um, send a link to the video. I have it recording on my hard drive, so I can't really send a link. I can't really send it over email because the file is too large. Um, and so YouTube is really just the best way to get it up. Okay. Let's move on. So again, this is not chapter 8, this is elimination reactions. So alkenes. They are carbon-carbon double bonds that involve sp2 hybridized carbons that are trigonal planar. Okay. They are made of a pi and a sigma bond. They do not conform. There is no single bond rotation on a double bond. Okay. So alkene stability, everything that you will ever need to know is right here on the test. When they ask you, rank the following alkenes in stability, here it is. Okay. Okay. Increasing substitution, increasing stability. Why geminal diols are more stable than trans? No idea. Geminal substitution is more stable than trans. I have no idea. I think it has to do with actually, yeah, I have no idea. Yeah, I just don't know. But that is the pattern. I doubt he's gonna go as far as know the difference between geminal and trans, but you will be asked to know the difference between cis and trans, and you will be asked to know the difference between disubstituted and trisubstituted and so on. Okay. Let me say that again. I doubt you'll need to know about the geminal, the gem, but you will likely need to know about the trans and the cis, as well as the general trend of going from unsubstituted to tetrasubstituted and the increasing stability that results. Okay. A, left or right? Okay, great. B. Okay, yep, right, right, and then C is gonna be left. As to why this was this was earlier. I'm just saying it again. Down to the right, leaving group ability. Before I go any further, as leaving group ability increases, the rate of reaction also increases. Okay. SN1, SN2, E1, E2. Increasing leaving group ability, increasing rate of reaction. Doesn't that sound like a very easily testable question? I would 100% expect that. 100%. It'll literally probably be like, here's a fluorine, rank the following in reactivity in SN1, SN2, E1, E2, and the only differences between the options are the leaving group. Okay. Okay. So this is a very testable question. Okay. When you see an elimination reaction, the very first thing that I want you to do is identify beta carbons. Okay. If that is so ugly. Alpha carbon. This is a beta carbon. Okay. For B, this, beta carbons. Okay. You need to be able to identify that. Make sense? Okay. And if you do not have, there's not a really a good example here, but say that you have this. These are two methyls in black. Okay. This is a beta carbon. Okay. But there's no beta hydrogen, so I cannot have an elimination product onto that carbon. Okay. Make sure that you identify that. These are just trends from chapter 3, but as we have a negative formal, a negative charge means a stronger base. Bases are less sort of prone to steric hindrance, and so we can kind of use that to our advantage. So like a good example of that is this, which is tert methoxide, and it is going to be a very strong sterically hindered base that, because of the steric hindrance, makes it non-nucleophilic. Okay. Okay. Any questions? Okay. Trend for basicity, up and to the left, which is just the opposite of acidity. Okay. So in elimination reaction, we need two things. Okay. A leaving group and a base. Okay. I'll say that again. For an elimination reaction, we need two things: a leaving group and a base. I'll say it again. For an elimination reaction, we need a leaving group and a base. Very, 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 very important. Okay. So it forms an alkene. And then for both E1 and E2, increasing substitution is going to increase the rate of reaction. Okay. Okay. For the E2 reaction, okay, it is going to be a concerted mechanism that is going to utilize a strong base, and the rate law is going to be bimolecular, and is going to include both the substrate and base. Okay. This is the first reaction that we'll see that has a very important regiochemical implication, I guess. And we'll get into that in a second. But for now, I do want to talk about a little bit of the stereochemistry involved. Okay. So what we will tackle today is the sort of simple version of the anti-periplanar, which is going to be a transdiaxial leaving group and hydrogen on a ring. Okay. Let's say I have this ring with this leaving group. All right. If I have a methyl here, and let's say NaOH, all right, will my alkene form here, or will it form over here? So from the rules that we know, in general, it'll form the most stable alkene, right? However, you have this requirement here that comes into to play with rings, where you need to have a transdiaxial leaving group and hydrogen. Okay. So let me just draw in this really quickly. All right. Do you see how this and this are trans to each other? Awesome. If I wanted to go down with my double bond, I couldn't because my hydrogen is actually out in front, right? And so that hydrogen in red and my halogen are cis, so they cannot react. They have to be transdiaxial. Okay. So the product is over here. And it will look like this. Okay. Okay. There is another application of this that involves taking your bond line, forming a Newman, taking that Newman, rotating it, or rotating the carbon on the back, and then taking that and then bringing it back to bond line, and then doing an elimination reaction to predict your product. However, it'll probably only show up as one question, and it takes like a year. It takes a massive amount of time to do. And so I'm really not too worried about it. Okay. 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 Here's the E2 mech. What you're going to see is you're going to see a proton transfer and lots of leaving group. Okay. Same step, concerted. Okay. A. I just want which one's the fastest. Yes. So left is going to be the fastest. Okay. The more substitution, the faster the rate of reaction. Okay. No. Do A. Is the double bond going to go up or to the left? Okay. Anybody else? Okay. All right. All right. Interesting. So I have two hydrogens here. One's in front. Okay, good, 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 good. Very good job. Good job, guys. This H and this chlorine are trans. And so even though this chlorine and this hydrogen are also trans, the alkene is more stable here, therefore it forms there. Okay. Okay. Does it make sense to everybody before I move on? Yeah, absolutely. So, this chlorine here is trans to this one, right? So it can happen in that direction. Now it may also be trans to this one. However, that is the worst wedge I think I've ever drawn. It's a bit better. Because if I draw the alkene here, it will be more stable. Okay, because it's more substituted. Therefore, the double bond forms between those two carbons. Okay. Of course. All right. Clear. All. Bam.
Oh,
Bam.
quick question.
Yes.
Sorry. Would the isopropyl group still be on a dash in the product, or would that be a line?
Just a line.
Okay.
Yeah, because it's planar, and so therefore everything needs to be on the same plane, right?
Okay, thank you.
Awesome. All right. Really, 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 really important. For a lot of you, the way you learned this was really more difficult than it had to be. I'll simplify it down to much easier. So there's two type possible products. There's the Zaitsev, there's the Hoffman. Okay. Zaitsev is the more stable, more substituted alkene, and the Hoffman is the less substituted, less stable alkene. Generally, the Zaitsev product will almost always predominate. Okay. Both will form, but the Zaitsev will be the major product. Okay. Except when the identity of the base is that of a sterically hindered one. Okay. But it gets simpler. It gets way simpler. If you see this or this, it's Hoffman. If it's not, it's Zaitsev. Okay. You may also see it as okay, or this. Okay. If you see those two, Hoffman. If you don't, Zaitsev. Okay. Okay. For A, do I put the double bond in black or blue? Okay, the answer is black. It will go to the more substituted product. Okay. Okay. Yeah, so that's pretty much it for the E2. I think the E2 is the most complex of the SN1, SN2, E1, and E2 reactions. Okay. All right. So, actually, hold up. Before we do that, do A. I want you to do the Hoffman. And while you guys are doing that, I'm gonna put up diisopropyl amide. Of diisopropylamide and tripetoxide. Tripetoxide's way more common in Oracle 1. No, just A. So black or blue. Remember, we're talking about the Hoffman product. Okay. Great. It's gonna be blue. Okay. It for the other answers, yes, it is for the Hoffman. It will be these. Okay. Always the least substituted alkene. Okay. Okay. Let me know. I'm gonna give you do you guys have any questions before we move on? I know the E2 reaction can be quite a bit. Because the camera is positioned in a way that I couldn't see it. And so therefore I didn't know those substituents were there. It's gonna be there. And you actually can't, there's no beta hydrogen here. So you just can't do it. Like it wouldn't even be the Zaitsev. Right. Okay. All right. All right. E1, weak base, unimolecular, carbocation intermediate. It's a stepwise mechanism, and the rate only takes into account the substrate. Okay. Okay. Also for E2, we want to use a polar aprotic solvent. For the E1, we want to use a polar aprotic solvent. The E1 doesn't really involve any interesting or fancy regiochemistry, and it doesn't involve really any stereochemistry. The E1 is pretty simple. All right. You've lost a leaving group, followed by proton transfer to give you your alkene, which will always be in the most substituted position. Okay. Again, we don't need to worry about this right now. Do I not? I do not. Okay. I need to change that. All right. I'm gonna open up the textbook real quick. the rest of the PowerPoint is nonsense. This flowchart was good when I first led the reviews, but they are kind of useless now. E2 is aprotic, right? Because think of it this way. If I have a base and a protic solvent, protic solvents can be deprotonated. So a strong base will deprotonate your solvent and be destroyed. Okay? You don't want that. What you can either do is you can do one of a few things. You can either use, like, if your base is OH, you can use water as a solvent to kind of help. But in general, no. You don't want a polar protic solvent and a strong base together. Okay. This chart here is this is all in the Word doc I gave you. This here, and memorize it, okay? And then this here, memorize that, okay? And then when you're on the test, when they're asking you what's the major product, plug and chug. To what? It's in the Word doc. Yeah, no, that Word doc I gave you should be pretty useful. Okay. So that's the slides. Let's do A. So what do you guys think it'll be? Will it be E1 or E2? You guys can't see that. Give me 1 second. A. Yep, this is going to go E2. Methoxide is a strong, negatively charged base that is going to drive for the E2 reaction. If I plug this into the chart, it would look like the substrate is tertiary with a strong base, and that should pop up as E2. Okay. 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 Any questions? And just a heads up, I'm asking any questions and then I'm going to go broach into a really high yield thing. Okay. It's like, don't leave if nobody asks questions. Okay. All right. So nobody seems to be asking questions. So what we're going to do now is, because you guys have stayed for literally 4 hours with me, and I appreciate that, what we are going to do is go chapter by chapter, and I want to talk about what I think will be the most high yield items from each one. Okay. All right. I made a list somewhere. Let me find it. So let's start with chapter 5. Yeah, I'm not going to find it in this mess. Chapter 5. I think there's going to be one question that's going to literally ask you, identify the chiral centers. It's just be like circle them. So just go through the molecule, circle the chiral centers, okay? There will likely be another question that's literally going to ask you, hey, is this R or S? It'll probably give you a molecule, point at 3 different carbons, and ask you R or S. And the answer choices will likely be different combinations of R and S, right? Most definitely there's a Fisher projection question. That's definitely going to be one of your FRQs, probably, right? There will definitely be a determine the relationship of these things, right? It'll give you like 2 compounds. It'll be like, okay, which of these things is enantiomers, diastereomers, yada 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 yada, right? Chances are they'll be like, here's a bunch of compounds. Which ones are meso? Just circle the ones that are meso. Identify which ones are chiral. Just use the that set of steps I gave you, and just look to see if something is kind of enantiomers. Okay. What else? Let me go pull up the textbook and I'll just talk. If he asks definitions, then like know the definitions, but don't know them. Don't worry about them. Okay. He might ask one optical activity question. What I want you to know is that if I have one enantiomer that rotates light 10 degrees to the right, the other enantiomer will rotate it 10 degrees to the left. Okay. Enantiomers rotate light opposite directions. And then naming. There will be a naming question. Okay, be ready for it. It will likely be multiple stereocenters, and you'll need to identify that and then use your parentheses accordingly. Okay. That's chapter 5. Chapter 6, definitions. He might ask you to maybe use delta G in one question. He might ask, identify this mechanism. He's likely going to ask you to understand an energy diagram. It'll be like, label the delta H on this graph, and then is it ENHO or exothermic? Other than that, most of the questions from 6 are likely going to be applied through 7. Okay, so 7. Nomenclature, definitely. I think that most of the questions asked from this chapter are going to be in the format of substrate, reagent, predict the product. Okay. So you're going to need to be able to look at a substrate and a reagent, use your chart that I gave you from the textbook, plug it in, figure out the mechanism, and then figure out the product. Okay. Rank the following compounds in speed of X. Definitely. Okay. Rank the following in nucleophiles in increasing nucleophilicity. For an E2, it might be like reagent reactant or substrate with this type of base, predict a product. One of the answer choices will be the Zaitsev, one will be the Hoffman, and then some variations of other stuff. And you'll need to be able to sniff that out. Okay. Nomenclature of alkenes is here. Know it. Know if I asked you to predict the product of an SN1, then I expect both enantiomers if there are two enantiomers. I expect you to write both diastereomers if there are two diastereomers. Understood? You guys need to keep that stereochemistry in mind. That is stupid points to lose. Okay? Okay. What else? Rank the following carbocations in increasing stability. Rank the following alkenes in increasing stability. Lots of ranking questions. Rank the following leaving groups in leaving group ability. And that's everything I can think of. Given a substrate and a reagent, predict the product and the rate law. What you'll need to do is take your substrate, your reagent, plug it to the chart in the book, the one with a bunch of colors, get that to spit out a mechanism, and then use the chart that I gave you that I made to know the rate law given the mechanism, and then you plug that in as your answer, and then you plug in the product as your answer. Make sense? Okay. There's really nothing else I can think of. Any questions? I'm trying to figure out how much I can tell you. Because I know like exactly what one will be. But that is cheating if I tell you. So I'm trying to figure out what I can tell you. Okay. I can tell you this. I can tell you that know your stereochemistry for SN1, and I can tell you to know that enantiomers rotate light in opposite directions. It is the same. It is basically going to be the same format. It's going to be that throughout the year, except for your final, which is probably going to be like a 70 question multiple choice test. And that's just my best guess. I didn't write the test. I don't actually know what's on it. I just have a really good idea. Yeah, absolutely. As an extra critic. Oh, yeah. Great save. Calculating enthalpy. That's one of those things where it's like, yes, this is absolutely 100% a question. Reaction rate problem one last time. What do you mean? Oh, like rank the following reactions and okay, I got you. I might give you a substrate and a reagent. Okay. I can then ask you to predict the product and to give me a rate law associated with that reaction. Okay. So be ready to do that. How do you do that? What you do is you use your substrate, you use your reagent, and you are going to plug that into the table with a bunch of colors. And then that should spit out a mechanism. Okay. You're going to use that mechanism and you are going to use the chart that I gave you. And you're going to use the chart that I gave you and the mechanism that you already know at that point to find the rate law. Okay. Make sense? Awesome. Any other questions? Okay. I'm going to do my best to try and get this uploaded as soon as I can. Again, yes. Again, I can't guarantee anything. You have to plug in, you have to write in your substrate. So whatever's given in the question, that's what needs to be there. Yes. I just published the document again. It's too late. Never mind. Any other questions? All right. Thank you guys so much for coming. I wish you guys the best of luck on Friday. If this next test is not moved, study hard. A lot of content, a lot of reactions, a lot of just stuff. Why would it be moved? Because we moved this test back a week. Like the test we're taking to like Friday got moved. So like you have less time for this next test. I'm sorry, the test after Friday, right? It's all good. It's all good. That's gonna be rough. It's a lot of content. So start studying for that soon. Okay. All right, guys. Best of luck, okay?